Welcome to my projectbazaar.com.
Now we discuss about the product for implementation of low power 8-bit multiplier using gate diffusion input logic. Next we see the abstract for the product. CMOS multiplier occupy substational area and power in digital circuits. To further optimize power and area, it is required to reduce the number of devices in design of multipliers. This can be implemented using a revised CMOS logic bias GDI technique. Circuits designed in GDI base are based on GDI basics cell, which allows us to apply more than one input of GDI based architectures. The common block of 8-bit multiplier in both GDI and CMOS designs. Both encoder is compiled for efficient generation of partial products. The partial product generation are either multiplicand and multiplier operation for depending on the output of both encoding. Wallace tree technique is to implement the full adder based architectures to reduce the addering architecture results and to implement the partial product generation unit. Both encoder is multiplier and the module consists of 8 XOR gate, 7 inverters and 8 AND gate functions in our overall architecture results. Multiplay is the most commonly used in circuit in digital device. Multiplication is one of the basic functions used in digital signal processing unit. Gate diffusion input logic reduces the power dissipation and area of digital circuits while maintaining low complexity of logic design. In this paper, GDA technique is used for low power design of 8-bit multiplier. Reduction in power and area can be achieved using the Booth encoding and Wallace tree technique, since they generate partial product efficiently and are most suited for multiplication of signed numbers and unsigned numbers. Multiplier design for GDA logic requires lesser number of devices compared to CMOS logic. Our GDA based multiplier logic is mainly developed for Xilinx project, and to implement the VHDL language to develop our 8-bit based GDA based multiplier architecture designs. Then to reduce the area and processing delay time for our architecture level. Next we see the flow diagram for the product. The input bits are applied to the GDA logic function. The GDA logic function one of the mux based architecture based on our selection carry selection process. This process mainly used to reduce the carry propagation time and to improve the processing speed for overall multiplying architecture, and to apply the GDA logic function in full adder architecture. These full adder architecture mainly developed for 2 XOR gates and the 1 mux 2 input 1 mux functions. These mux functions mainly selected by the carry selection processing time. Then to select the carry selection and to apply the processing result for full adder architecture carry functions. This function to improve the processing time, and this architecture to apply the 8-bit multiplier architecture. This 8-bit multiplying architecture mainly used to do structural modeling process. We implement the structure modeling process and to develop the partial product generation unit. This partial product generation unit mainly based on half adder and full adder addition architecture based on the tree formations. These addition architecture to improve the addition process and to enhance the processing time based on our architecture development. These are the PPG unit process. This PPG unit process to apply the final to display the results for 8-bit multiplying results. These multiplying results to generate the 16-bit output results for our the overall GDI based multiplier architecture, and to finally calculate the simulation and synthesis results based on our 8-bit GDI based multiplier architecture result. This is our overall flow diagram for GDI based multiplier architecture result. Finally we see the output for the product. First we run the MIMO multiplying process for Xilinx ISC project. This multiplayer architecture was developed in VHDL language and to use the structural modeling process for our VHDL coding designs. Then select the multiplier and process to select the simulation and to run the simulate behavior model. Then we open the iSim project navigator. This project navigator mainly used to simulate our processing result with the binary form. Then we apply the input for binary result in our architecture. Any of binary input to apply the A and B multiplier and multiplicand process. Then to run the time specified on the toolbar, just we apply the output result for multiplier architecture. Then close the simulation process and to select the implementation process. This implementation process to describe the RTL and technological schematic process. This RTL then to add the process and to create the creative schematic process. This is our diagrammatic representation. This diagram mainly is to what are the logical blocks placed in our overall multiplying architecture. This is our partial part generation unit. This is the architecture for full adder and half adder based multiplier. This is the to XOR weight and to select some Mux logic to apply the GDA based applications. For our the 8-bit GDA based multiplier architecture, this is our the technological diagram. This technology diagram mainly used to what are the lookup table and input and output wire connections, then input and output buffer connections based on our GDA based multiplier architecture. Then we go to the design summary process. This design summary process mainly used to simulate synthesis the synthesis report. This synthesis report used to what are the device utilization in our overall GDA based multiplier architecture and to calculate the processing time for overall multiplying architecture in GDA based multiplier architecture functions. This is the processing time for combinational path delay functions for overall architecture results.